Hey everyone, and a special welcome to all the ELET 342 students tuning into this explainer. If you're studying communications circuits right now, well, you already know the drill. Designing, building, and actually testing these systems, it's incredibly complex. It takes a massive amount of time. But today, we're looking at a tool that is literally going to flip your entire workflow upside down. It's called GNU Radio. By the time we wrap up here, you're going to see exactly how this software takes all those heavy theoretical concepts from your class and brings them to life right there on your laptop. So let's kick things off with a frustration I know we all share. Think about the traditional way of developing a radio communication device. You have to build out specialized physical hardware, right? You need one specific circuit just to detect a signal, a totally different integrated circuit to decode it, and then you're stuck debugging the whole shebang with super expensive lab equipment. And heaven forbid you want to test a slightly different filter or, try out a new modulation technique, you're basically forced to physically redesign and rewire the entire board. It's tedious. But what if you just didn't have to do that? What if you never had to build a brand new hardware circuit for every single little tweak? Well, that exact frustration, it's what sparked a massive revolution in engineering. We're talking about the huge shift from traditional radio over to software-defined radio, or SDR. And it is exactly what it sounds like. SDR takes all that heavy lifting, all that messy analog signal processing, and just scoops it up and moves it directly onto a computer. So instead of being totally locked into costly, rigid hardware, you process your radio signals using flexible, scalable, completely reusable software algorithms. A clunky physical circuit board gets replaced by just a few lines of code. It's pretty amazing. But to really grasp how this all works, we've got to go back to square one. Because to do any signal processing in software, your signal actually has to be digital. But, as we know, signals always start out there in the messy, physical, analog world. Think about human speech. When you talk, your vocal cords are just creating waves of varying air pressure. And when those sound waves hit a microphone, that mic's job is to convert that changing pressure into a continuous electrical signal, a variable voltage. At that specific moment, it is 100% purely analog. But here's the catch. Computers simply cannot handle smooth, continuous analog signals. They just don't speak that language. So we have to digitize them. And making a signal digital really just means two very specific things. First, it can only take on a limited, discrete set of values. And second, it only exists at specific, discrete points in time. So we're essentially taking that smooth, continuous analog wave and chopping it up into specific points mapped onto a grid. That digital signal is now nothing more than a sequence of numbers. We call those numbers samples. All right, so let's break down exactly how these physical waves actually cross over into the computer domain, because this is absolutely crucial. It happens in three distinct steps. Step one, you start with your physical quantity, that analog voltage we just talked about. Step two, you run that voltage straight through an analog to digital converter, or ADC. This little device essentially takes snapshots, sampling the voltage at fixed intervals of time. Which leads us to step three, you are left with your digital samples, just raw numbers. And the beauty is, once you have those numbers, your computer can do whatever you want with them. You can apply digital filters, compress the data, recognize speech, all purely in software. This right here is the absolute bedrock of digital signal processing, or DSP. Okay, so how does this tie directly into the radio transmissions you're dissecting in ELET 3402? Well, the exact same principles we just walked through for sound waves apply perfectly to radio waves. Only this time, instead of a microphone capturing sound, you have an antenna capturing electromagnetic waves and converting them into that varying electrical voltage. Now, in radio communications, this electrical signal is riding on a carrier frequency, usually way up in the megahertz or even gigahertz range. But once that high-frequency signal is captured and stepped down by your receiver, it goes right into an ADC and gets digitized. Once it's digital, the software takes the wheel. And that brings us to the star of the show, GNU Radio. Think of this as your ultimate digital laboratory. Because let's be real, writing all these complex signal processing algorithms from scratch is a massive headache. You'd have to manage data flow between processing blocks, optimize all the code, build the user interfaces. It's a lot.
GNU Radio completely bypasses that. It gives you this incredibly intuitive visual editor that handles all the messy data movement for you behind the scenes. You literally just drop in highly optimized, pre-written processing blocks and connect them together to build your entire radio system.
Within GNU Radio, this whole visual setup is called a flow graph. And a flow graph is exactly what it sounds like, a complete graph of connected processing blocks that makes up a full radio application. I like to think of them as digital Lego blocks for engineers. Each individual block handles one specific stage of processing. Maybe one block filters out noise, another corrects signal phase, another analyzes the spectrum, and another detects a modulation pattern. You just snap them together using simple arrows, and GNU Radio automatically flows your signal data perfectly from one block to the next.
Now, if you are a communications circuit student, this is where it gets really fun, because the GNU Radio environment maps almost perfectly onto your current syllabus. When you open up the standard library in the software, you are going to see blocks categorized by the exact concepts you're sweating over in class right now. We're talking waveform generators, modulators for AM and FM, a ridiculously huge variety of filters, and even channel models so you can simulate real-world interference. You even get Fourier analysis blocks for really deep spectrum analysis. All these core building blocks are just sitting there ready and waiting for you to play with.
And the practical, real-world applications here are honestly staggering. You absolutely do not need a massive, expensive lab to test out advanced systems anymore. You can use incredibly cheap consumer-grade hardware, like those little digital TV receivers known as RTL SDR devices. You can use one of those to pull actual real-world radio signals right out of the air and into your laptop. Or, hey, if you don't have any hardware at all, it doesn't matter. You can run these complex flow graphs entirely in a software simulation. You can literally design, simulate, and deploy a highly capable radio system without ever once picking up a soldering iron. So, to really boil it down, the official documentation describes GNU Radio as a framework for the development of signal processing blocks. Basically, a giant box of building blocks. It is not just some rigid, out-of-the-box app designed for one single standard. Not at all. It is a highly modular, open-source ecosystem. It's designed to empower you to build virtually any band-limited communication standard you can dream up, transforming incredibly complex hardware processing into simple, modular software. So as we wrap up this explainer, I want to leave you with a question to chew on. Are you ready to stop rewiring rigid circuits and start building your own unlimited digital radio laboratory? Because those theories you're studying in ELET 3402, they aren't just dry equations on a chalkboard. They are the exact algorithms powering modern software-defined radios right now. By firing up GNU Radio, you can take that knowledge and immediately use it to visualize, simulate, and actually build the future of wireless communications right there on your computer. Thanks for hanging out with me for this explainer, and seriously, have fun building